my sweet fizz heads. Today, since I'm not with you, I plan to post this on Monday, I want to briefly introduce conservation of linear momentum. So, Newton called this quantity of motion. He called momentum, but quantity of motion. And he defined it with this P is the mass times the velocity. Okay, so momentum, linear momentum, is the mass, scalar quantity, times this vector quantity, the velocity. Of course, you understand the units clearly enough, and that's our basic definition you've seen before when we introduced Newton's second law. So recall, for a particle of constant mass, okay, that the time derivative of this momentum, or mass times velocity, if the mass is constant, you can just factor that out, and you get the mass times acceleration. We said that that was the net force. This is kind of an operational definition, and another way to write Newton's second law is seen right here, that the net force acting on a single particle is the time rate of change of the momentum. You can write it that way. In fact, that's the way Newton originally wrote this. So we've also gone through that argument by summing up individual particles and thinking about a system, right? That we can rewrite for a system that the net external force, not talking about the internal forces, because remember all those would cancel, but the net external force is the total mass of the system times the acceleration of the center of mass. So we can go through the same kind of argument, and I'll do some more of these details with you on Tuesday, along with a number of examples. But we can write down that the momentum of a system, so summing all this stuff up, is the total momentum, or total mass, so it sounds like momentum, total mass times the velocity of the center of mass. Okay. And if there's a constant mass, then we can factor that out, do this time derivative, and we see that the net external force again is that time rate of change of the momentum of the system. So this leads directly to the conservation of linear momentum, the big concept for this chapter 8 for our next unit here. So notice that if the net external force is 0, then the momentum of the system must be constant. That's conservation of linear momentum. Now, of course, we need to flesh out exactly in what sort of situations does that happen, and what can we do with it, and what sort of problems can we solve, and all those details are things that we'll work out. Now, the kinds of problems often involve collisions. They tend to be the ones that we can use this concept of conservation of linear momentum to solve. So if you have two particles and they collide, what does that mean? Well, we define that somewhat loosely, but talking about large forces or interactions between two objects over some brief time interval. These are impulsive forces. And so we define an impulse as the integral from time 1 to time 2 of the force over this short time interval. Graphically, if we're looking at a situation like this, we have some large force over a small time interval. And notice that we can also define an average force that would give you basically the same area, right? So the area of the little green rectangle, the average force times that time interval, would be the same as the impulse, which you're integrating over a specific force, okay, that varies with time, a large force over that same time interval. So, summing up the impulse stuff, we can also write that the net external impulse is the average net external force times some little time interval, and that would be the change in the momentum of the system. So, more details and examples coming to you on Tuesday. That's it for now.